Assalamu alaikum. Today we are going to discuss controllability. Basically, we are discussing the pole placement technique. Or topology. Or in some books, they are also been mentioned as pole assignment. Basically, we are placing the closed loop poles to a desired location in the S-plane. So that is why they are sometimes being called as a pole assignment topology as well. So bottom idea is each and every, the difference between the conventional feedback and this pole placement topology, which is based on the state feedback technique, is that from each and every state each and every state is been controlled by a input U. Okay, and based on the select the gains, the feedback gains, those help us to control the state, and in turn, actually, we are placing the pole in a desired location. So basically, x dot equal to a minus bkx plus br. So which is coming from our original equation, x dot equal to ax plus bu. And u is been taken as a minus kx plus r. So r is regular input and k is basically our state feedback gains. So each and every state is fed back to the input, or in turn, we are actually controlling each and every state to place the poles to a desired location, to a corresponding desired locations in the S-plane. So whether we can apply this pole placement technique to each and every system or not, for that actually this topic is being introduced, that is controllability. So if the system is controllable, only then this pole placement topology or pole assignment topology can be applied to a system. So now come formally to the definition. The definition says that if an input U that can be found for a system that takes every state variable X from a desired initial state to a desired final state, then the system is controllable. Okay, in essence, we have to place the poles wherever we want in the S-plane. And how it is possible? If each and every state variable is accessible by our input. So in that case, we can say that our system is basically controllable and the pole placement technique can be applied to the system. So if your system is represented, this is part of also the first way to find out that is actually controllability by inspection. Controllability by inspection. So basically, if you have a decoupled system with minus a1 0 0 0 minus a2 0 0 0 minus a3, this is your system matrix with your x plus you have b, which is 1 1 1. R or U, whatever you like. So if this is a scenario, now if you write the equation x1 dot equal to minus a1 x1 plus U. So x1 is only dependent, x1 dot is only dependent on x1 variable. So that is why they're decoupled. X2 dot equal to minus a2 x2 plus U. And x3 dot equal to minus a3 x3 plus U. So each and every state has been controlled by the input U. And if you want to draw it in diagram, then what we are going to see is that each and every state is somehow being controlled by the input. We have been able to find an input so that each and every state can be controlled. Okay, so this is 1 by s, 1 by s, or 1 by s integrators. Then you have input, say u goes here directly with the gain 1, goes here directly with the gain 1. This one as well goes with the gain 1. And this is your output, which can have different gains, but assume that those are also 1. So now this is your x1, not dot. Other side of the integrator will be actually x1 dot. This is x2, x2 dot. This is x3, x3 dot. So somehow, if one of the link is missing, say this one is missing, and this is also not available, this portion. Okay, so then is your system still controllable? Can we control the state x1 anymore by some input? So definitely not. And how we figured it out? X1 dot equal to minus x1 0 0 0 minus a minus a1 0 0 0 minus a1 0 0 0 minus a3 x plus you have 0 1 1. There you have u. So basically from the B matrix here we can identify whether the system is controllable or not. Okay, so based on the B matrix, whether any rows in the B matrix are uh, zero or not, based on that we can do that. But for that, one thing is for sure, and that is your system has to have distinct eigenvalues, and the system matrix has to be diagonal. And if B matrix, if it is represented this way, diagonal, with a diagonal system matrix, and eigenvalues are distinct, that is minus a1 minus a2 minus a3. And in under this circumstance, if you look at the B matrix and one of the row is 0, then your system is, if any one of the row is 0 or multiple, so your system is uncontrollable. This is by inspection. Now, this condition is quite rigid, that the system has to be represented in the parallel form, or eigenvalues have to be distinct, the diagonal system matrix you have, and the system has to be decoupled, as we said, that x1 dot only depends on x1, x2 dot only depends on x2, and x3 dot only depends on x3. If all this condition is true, only then looking at the B matrix, we can identify whether the system is controllable or not. So the second method, which is more common, whether you're represented in the parallel form or not, it doesn't make any difference. So that is actually by using a matrix that is called controllability matrix. So the controllability matrix, we call this is CM, controllability matrix, and which is given as B times AB, A square B, and it goes on up to A n minus 1B. If your system that is represented as x dot equal to ax plus bu is of order n. So nth order x system that is represented by x dot equal to ax plus bu, and from that one you find your controllability matrix CM, and the rank of CM is same as the order, that is n as well. Only then we can say that our system is controllable. So let us solve one problem. The problem will make things easier to understand what is actually happening here, what we are trying to say here. So example 12.2. signal flow graph is given for a particular system. Let me draw it first, then we'll try to explain it, inshallah. Okay, so this is our input U. This is -1. This is your -2. Okay, so this we can term this one as x1. So this is your x2. This is your x3. So this is x1 dot, x2 dot, and x3 dot. So based on this one, we can easily write the equation. Some things, some of the things those are missing. Is basically you can also say this is 1, this is minus, this is 10, this is -10. Okay, so now if we find out the equation, that is x1 or x dot equal to basically how they're related, x1 dot, x2 dot, x3 dot. So basically x1 dot, you can easily see here that x1 dot is minus x1 plus x2. So minus x1 plus x2 and no link with x3. Similarly, x2 dot is only linked with x2 dot with -1. It has no relation with x1 or x3, and x3 dot is only linked with x3. So you can write in this way, and your B matrix is definitely the x1 is linked with, and x1 is not linked with input, so the 0, and x2 is linked with input. So now this is your B matrix. Now by inspection, what you can see is that B matrix is having a row 0. So by inspection, it should be, and the system should be uncontrollable. But somehow, since the condition that has been given is the system is not, it doesn't have distinct real pole or real eigenvalues, rather it has repeated poles. As you can see, 2 pole you have at -1, 1 pole at -2. So that is why the rules of your by inspection is not valid in this case. So what you have to do is you have to form the matrix, controllability matrix CM, that is B, AB, A square B. So B is straightforward as it is coming from the equation. So 0, 1, 1. The AB is you just multiply A with B. So basically from this one, you can easily figure it out. Okay, so 0 into -1 is 0, 1 into 1 is 1, 1 is 0. So basically it will be 1. Then next row, -1. The next will be 0 into 0. So basically -2. Now this one is this. Now this one is this. Now A square B. It seems like you have to find out the square, then multiply with B. It's not the case. Rather, you're multiplying A with AB. AB is already, you figure out this is your AB. So you have to multiply A matrix with this value. So 1 into -1 is -1, 1 into -1 is -1. So basically -2. Then similarly, minus 1 into 0. Then minus 1 into minus 1 is 1. Then you have next one is 0, 0, and minus 2 is plus 4. So this is your controllability matrix CM. So next, you have to find out the rank of CM, and the procedure of finding the rank is basically finding the determinant of your matrix. So find the determinant, that is 0 into minus 1, minus 4 into minus 4 plus 2. Since we multiply 0, it doesn't make any difference. 4 minus 1, minus 2 plus 1. So eventually, minus 3 plus 2 is equal to minus 1. So the rank, what is the definition of the rank? Rank is finding a square matrix out of your system matrix A. From that one, what is the square matrix that you can find that gives you a non-zero value? So if you find the determinant of A, determinant of controllability matrix, which is, even though you say A, but it can be something else as well. Any matrix that you have, say matrix M. So you find the determinant of M, okay? And if it gives you, to find the rank of it, if it gives you, say if it is a 3 into 3 matrix, it was, and the rank was, and the system was of order 3, okay? And your rank of the determinant is not 0, then your system's rank is also 3. Okay, let me try to make it a bit more clear if possible. That is, you have a 3 into 3 matrix with values, and like this, say this is your controllability matrix, CM. Now, if you find the determinant of CM or the magnitude of CM, then and you find this is non-zero, that means it is of rank 3. Now, but in case that you find that it is 0, then you have to find out a square matrix out of this one, either this square or this square. So any square that gives a square matrix 22 matrix that gives a non-zero, that will be the next order if the first case was 0. So the rank will be 2. And if that is also not available, only one value is non-zero, then your rank will be 1. So basically, what is the size of the square matrix that you can obtain that gives you non-zero value or non-singular value? That is your rank. So maximum size is the rank of your system. So in our particular case, if the rank of the matrix is equal to the order of the system, then your system is controllable. Otherwise, if the rank is lower than the order of the system is not controllable. And if system is only controllable, then you can use the pole placement technique. So pole placement is only applicable to a system that is controllable. Okay. So checking by inspection or by using the controllability matrix, inshallah. So this is the conclusion. Let's discuss the other design techniques in the next class, inshallah.